All right, well, good morning. Welcome to another fun-filled day of calculus. The quizzes are done. I did grade those and put them into Gradebook. You should also have gotten some comments on them. Basically, what I did was I gave you your scores on each of the problems and made a little comment if you missed some points, or I wrote them on the actual file that you put in. If you go back and you look at those, you can see that I can use my stylus and create comments and stuff like that. So make sure you look at those as well. But I do want to talk about a few things from it. So I'm going to go ahead and share a whiteboard here so that we can, so I can show you what I'm talking about. The first question about finding the inverse, most people did fine on. There were very few issues with that. It mostly ended up being small algebra. So I'm not going to go over that one, but if you do have questions, please let me know. But I do want to talk about number 2. And number 2, we had a function g of x that was x cubed plus 2x. And I asked you to approximate the instantaneous rate of change at x equals 1. Okay, so first things, when it says approximate, that doesn't mean we're going to get the exact value. It turns out the exact value for this one is 5, and we'll actually do that today. I'll show you how we can find it exactly, excuse me, but we're going to get something near that. And if we want to get the rate of change, remember that the rate of change is the slope. This is kind of a key thing. Anytime you see rate of change, you want to think slope. And so for the average, this is the slope of a secant line. And for the instantaneous, it's the slope of the tangent line. Now, we don't have the tools yet to get the instantaneous. Well, that's not quite true because I just showed you at the very end last time. By using limits, basically bringing those 2 points in, we'll kind of refresh our memory about that. So we just barely got that. We didn't have that before. So what we're going to do is we're going to approximate it by using an average, which means we need 2 points. Now, one of the points I'm going to use is just the point itself at 1. So I know that if I plug in 1, I'm going to get 1 cubed times 2 times 1, which is 3. So there's a point on my graph that's 1, 3. Now, I need to get another point to get my approximation. And I don't want to go very far away. Like I could plug in x equals 2. But that's a pretty big step. And my approximation is not going to be super good there, most likely. So I'm going to go with a smaller step. I'm going to go with 1.1. Now, you may, if you go back and you look at the quiz, I mentioned how you could pick your second point however you feel appropriate. So some people use 1.1, some people use 0.99. There was one of you that used 0.99 and 1.1 instead of 1. I mean, that's cool, right? Those are all pretty good approximations because we're not very far away from the point where we're looking. But if I were to plug that in, right, get my 1.1 cubed plus 2 times 1.1, excuse me, this ends up being 1.331 plus 2.2, which is 3.531. So there's another point on our graph that's 1.1 comma 3.531. All right, so now what I'm going to do is I'm going to take these 2 points, this one and this one, and I'm going to find the slope of the line that connects those two. So the slope formula, remember, is the change in y over the change in x. So I'll have 3.531 minus 3 divided by 1.1 minus 1. So that's 0.531 over 0.1. Just have to move the decimal 1 spot. And I get 5.31. So what I know is that the instantaneous rate of change is going to be near 5.31. So that's what I get using these 2 points. If you use 2 different points, you're going to get a different m value. But the closer these 2 points are together, and basically, so the closer they are to actually being at 1, the better this approximation, right? So like if I had used 1.01 and taken whatever that y was, put those in here, the number that came out would have been closer to my actual value, which again, like I said, was 5. All right, so that's kind of the approach I was hoping to see, is creating 2 points that are relatively close together and finding their slope. That's how we approximate an instantaneous rate of change. But the whole point of calculus is now we're going to figure out a way to get the instantaneous rate of change, not an approximation. All right, so questions on that one? Does that make a little more sense? Kind of what I was looking for? I will take silence as yes. Okay, so then number 3, again, went pretty well with the rules of logs. Most of you saw how to put that together. The one thing I'm going to remind you is that when you have a positive log, that stuff goes on top. And if you have a negative log, that stuff goes on the bottom once you put it all together as 1, right? And there should have just been 1 log with a fraction inside. And then number 4, let me just remind you guys about a couple of things here with number 4. Trig tends to be the thing that gets people the most. So let me just go back to reminding you about a little bit of trig here. So when you have a sine or cosine, I'm going to go ahead and write it as a cosine. Okay, so here's a generic one. Now you can change this to sine and it doesn't change anything else that I'm going to tell you here. To find amplitude, that's always the absolute value of A. Amplitude is always positive, so it's the absolute value of A. The period is going to be 2 pi divided by whatever the multiplier is on x, so that tells us how frequently it repeats. The phase shift, this is always C over B. So it's whatever that's being added inside, we have to divide by this multiplier. And just remember that if it's an addition, this is a shift to the left. If it's a subtraction, it's the shift to the right. So it does the opposite of what you think. And then this guy D, I don't think the homework problems had anything with it, but I like to just be complete. D is a vertical shift. So it just picks up the graph and moves it up or down. And this does exactly what you think. If it's adding, you move it up that far. If you subtract, you move it down. So these are the, in general, how you do any one of these. So being equipped with this makes it so that when we have a specific problem, like the one that was on the quiz, which was a -2 cosine of 3x plus pi, right? So here you go. So your amplitude, absolute value of -2, which is 2. Your period is 2 pi over b. Well, the b is 3, so it's 2 pi over 3. And then the phase shift is going to be pi over 3. But it is important that when you have a phase shift, you describe which direction it goes. I know that some books and things will attach a sign to it, a plus or minus sign to it. If you are someone who learned that way, this should be a negative, right? If you're not, you should just say, okay, it's a pi over 3 to the left because of that addition. And that definitely matters. You take a function and you shift it left versus right, you can get something that looks completely different. But sometimes with trig functions, the left or right shift doesn't actually matter because you end up getting to be the same place just due to the period, right? The repetition that's in the trig functions. But in general, it's good to remember to attach some sort of a designation of which way it's going. All right, so that was the other one that caused a little bit of an issue, so I just kind of wanted to rehash that real quick. All right, so any questions on that one?
So you're saying that the phase shift could either be pi over 3 to the left or negative pi over 3?
Yeah, if you had written negative pi over 3, I would have accepted that. I don't, like me personally, I don't do that. I don't like attaching pluses and minuses. I like to just describe what's going on, you know, saying left or right. But as long as you gave me some sort of indication that it was going to the left, I called that good. All right, any other questions on that? Okay, well, so like I said, those grades are in, so you should see them on the gradebook and Canvas. I also just want to remind you that I will drop everybody's lowest quiz score. So if you took this quiz and you're like, oh man, I got a 14 out of 20 and I'm not happy with that, that's all right, right? As long as you do better than that going forward, this one will go away. But I will say that in general, this went well. I think the average for the class was a 16 point something out of 20, which you know, is a B. So in general, lots of A's and B's on this thing. I wasn't too concerned, other than the fact that there were some sort of common issues like on this one and question number 2. Okay, well, let me stop sharing then. And then the other thing I want to ask before I jump to the whiteboard is, are there any homework questions? Anything out from the homework that we want to look at? All right, that's pretty much what I figured, since homework was due Monday night, and the next set's not due for another 5 days. But don't forget to get in there and work on it, and I'm sure you'll have questions for me next time. All right, well, let me go ahead and jump over to the whiteboard then. So I'm going to go ahead and stop this video for switch screens, and I'll see you at the whiteboard in just 1 second. Yeah, it might help if I hit unmute, huh? Thanks for that, Aaliyah. So let me just kind of remind you where we are and what's going on. But right now, we're getting ready to dive into calculus. Like up to this point, it's probably been a little bit boring, a little bit blah, because we've just sort of been setting the table, right? I started by reminding you guys of some of the things that are important from pre-calculus. And then I introduce you to things like limits and continuity, and they probably felt like, oh, all right, so yay, it's something new. But those are the tools that we're going to use to create the calculus. So this is when it gets exciting. This is when we start learning this revolutionary idea that changed mathematics completely. All right, so last time I showed you how we were going to go ahead and find the slope of a tangent line or an instantaneous rate of change. So let me just remind you about that and show you where we were last time. Give me a second here. I apologize. My screen is slipping a little bit. Let's see if I can fix that touch. All right, I think that's a little bit better. Okay, so here was the idea. Let me start again with a picture. Love drawing the pictures to help you see what's going on. But we've got some sort of function here, and we're looking for an instantaneous rate of change at some point. So let's pick that point right here. We'll call it C. And so I want to know right here, what is the instantaneous rate of change? So another way of thinking about that is saying, I want to know the slope of the tangent line. But the problem is a tangent line only touches this graph at this one point, right? It just grazes it. So I only have 1 point, and I can't find a slope with just 1 point, right? Like go back to pre-calc at some point when you were learning about lines. If you were ever given a question on an exam that just said, hey, find the slope of the line that goes through the point 1, 3, you'd gone up to your professor, your teacher, and been like, I don't have enough information. I need to have a second point. So what we do is we create a second point. So we'll take a point that's somewhere out here. And we'll use those two to create a secant line. And we know that that secant line is a good approximation. So kind of like quiz question number 2. And then, of course, the way that we can make this a better approximation is by bringing that second point in. And basically, we want to bring that second point in so far that they are basically the same point. They can't be the same point, but we want them to be just ever so close. So the way that we got to that was by using limits. And so we had 2 forms for finding the slope of this tangent line. Okay, so I'm going to write this m tan, so slope of the tangent line. We saw that that was a limit as t goes to, well, there were 2 of them. So we'll do the first one. The limit as h goes to 0 of f of c plus h minus f of c over h. So looking at this fraction, just realize that it's a slope. It's a change in y over a change in x. And what that h was the distance from C to that second point. And so we're just saying, hey, let's get that distance between those two to be basically 0. All right, so that was one form, but we saw that there was another way of thinking about it. So I'm going to put here or. The other way of thinking about it was taking a limit, but not thinking about the distance between them, but instead thinking about this second point, which I'll call, say, x. And so this one would be the limit as x goes to c of f of x minus f of c over x minus c. So again, this is slope. This is the change in y over a change in x. And what we're doing in this case is instead of saying, let's make the gap between them disappear, we're saying, let's bring that second point to the first point. So they're really getting to the same idea. It's just 2 slightly different viewpoints. And we have these 2 because sometimes one is easier to use than the other, and you'll see them both pop up. I primarily use the first one. I find that one's a little bit easier to do mathematically. So I'll use this first one primarily, but there will definitely be times where I jump in with this second one because it's a little bit easier to do the specific problem that we're looking at. All right, so know these. Okay, know these, put these in your head. And this thing right here, this fraction, it has a name, and I want to go ahead and write it here so that when I mention it or when you read it or when there's a homework problem that says something about it, you know what we're talking about. But we call this the difference quotient. And in the classical style of mathematicians, we name things exactly what they are. It's a quotient, means division. It's made up of differences, right? We're subtracting things on top and bottom. So if you ever see that phrase, difference quotient, or you hear me say difference quotient, just realize it's the, oh, we're finding the slope of a secant line, right? It's that slope that then becomes the slope of the tangent line if we do the limit. All right, so this is where we got last time. Hopefully you all kind of remember this. And so what I want to do is actually just do a few examples of these. I know we got to one last time. I think we did x squared. But I want to show you some more just so you can kind of get comfortable with what we're doing here. And you'll also see why we talk so much about limits, because every time we do one of these, we're going to get a limit. And that limit is going to require using some of the techniques that we did before.
Could you quickly just describe in words one more time what each of those really means?
Sure. All right, so so when you say each of those, you mean the two different forms?
Yeah.
Yeah, okay. So let's look at this top one again. So h is the distance between the point where we want to be. Okay, think about this blue one, the C. That's where we want to know instantaneous rate of change. Okay. And then there's another point that's over here that we're using to create a secant line. But having those 2 points far away from each other doesn't really help, right? The closer they get, the better the approximation is. And in fact, I would love for those 2 points to actually be right together, right? But I can't have them exactly the same, because then I have just 1 point and I can't actually do the slope, right? So I need to have a second point. So I'm going to create the second point and then calculate the slope. So slope is change in y over change in x. All right, so think about these 2 points. The change in their x coordinates, the difference in their x coordinates is h. That's how I'm defining it, right? So that's why on the bottom here, I've got h.
I guess I'm mostly confused about, sorry, why h is going to 0, because doesn't that mean as x is going to 0, which is not where we are?
Nope, it's not saying that x is going to 0, because h is the gap between these 2 points. I'm just saying, let's make that gap disappear. Okay, so just think about h as, that's the step I'm taking to go to the next point. I'm just making it so that that step I'm taking is getting smaller and smaller and smaller, so that eventually it's like I'm not even taking a step. Okay, so that's why there's an h down here, because that's my horizontal shift. And I want that horizontal shift to basically disappear. And then on top, this is just the y coordinates, right? We get the y coordinates by plugging in our x's. The one is plugging in c, and the other one is c plus h, because again, h is telling me how far to go away from c. So that's that one. That's how that guy plays out. The second one is the same idea. It's a change in y over change in x. And I think you can see it a little bit more clearly with this fraction. Right? When you see f of x minus f of c and x minus c, you can see the delta y, delta x, right? But now what we're doing is we're saying, let's take that x, which was that second point, and let's make that second point get closer to the first. And in essence, that's saying the same thing, right? If now, instead of me saying, I'm going to take a step, now if I'm going to say, well, let me bring my front foot closer to my back foot, that's exactly the same as saying, take a smaller step. Okay, so it's getting to the same idea. We're just thinking about it 2 different ways. The first one's saying, make the difference in those 2 points nothing. Right? Make it so that there's no difference in those points. This one's saying, bring the second point to the first point. Same. So does that make a little more sense, Leah? Yeah, okay, cool. All right, so I think I did x squared last time. So let's play with this. Let's play with some other functions, and let's see if we can get an idea of what's going on when we're going somewhere else. So let's try this. Let's look at f of x equals the square root of x. And let's find the instantaneous rate of change, or the slope of the tangent line. So I'll go ahead and write here the slope of the tangent line at x equals 4. So I know I got a bit of glare coming up, so I'm going to skip down a little bit here. But here's another function. I'm giving you a point where I want to be, and I want to see if I can figure out the slope of the tangent line. Okay, so we have two choices of which one to use. It doesn't really matter. They're both going to do the same thing. And I think, again, with this one, I'm going to show you how both of them work and give us exactly the same value. I know I did that with x squared. I'm going to do that again here with the square root of x, just so that you can see it. All right, so let's go to the first one. If we use the first form, so that instantaneous rate of change, or that slope, it's going to be the square root of 4 plus h minus the square root of 4 divided by h. And we're going to take the limit as h goes to 0 of this. So just look at those, and you can see how I'm just replacing in here my specific function and the point, right? The specific function was the square root, right? So f was square root. That's why we're seeing square roots. And then the c, well, that was 4. That's the point where I'm interested in. So that's what that one would look like. The other one, so let me put a big or, because remember the other option is if we use the second form, it's going to be the limit as x approaches 4 of the square root of x minus the square root of 4 divided by x minus 4. So same deal. I'm just replacing in the c's with 4 and the f with the square root. So hopefully you can see with both of these how we're doing exactly the same thing. We're just using this form. So you're going to get really comfortable with these forms because you're going to use them a lot. Whatever the function is, we just go for it. All right, so actually, here's what we're going to do. Instead of running both of them, let's just do one of them. And which one do you guys want to do? Which one do you think is going to be easier? The first one or the second one? Or is it the same, and so it doesn't really matter?
The same.
Yeah, pretty much the same, right? Like either way, we're going to have to rationalize. I recognize that we're going to have to rationalize because of the square roots. I mentioned last time, I'm going to remind you that there's no reason ever, when you've got one of these limits, to actually plug in your value, right? When we do limits, our first go-to always is plug that number in. I'll just tell you that every time we're doing one of these with the difference quotient, every time you're going to get 0 over 0. So don't bother. Instead, dive right into whatever our algebra step needs to be. Okay, so we're going to have to rationalize either way. And since we're going to have to rationalize, yeah, I don't know. Let's just take the first one, see how it goes. So the very first one, if we take that limit, let me calculate, let's take care of the square root of 4. Let's at least simplify that. So we've got the limit as h goes to 0 of the square root of 4 plus h minus 2 all over h. So to rationalize, I need the conjugate. I'm going to multiply top and bottom by the conjugate, which is going to be the square root of 4 plus h plus 2. So I just have to put those on top and bottom. So when I distribute, I'm just going to distribute on the top. If I multiply that out, it's a difference of squares. I get 4 plus h minus 4 over h times that conjugate. Notice that on top, the 4's cancel. So I'm left with the limit as h goes to 0 of h over h times this stuff. And now I can cancel those h's. So we've got the limit as h goes to 0 of 1 over the square root of 4 plus h plus 2. So all of this was algebra. Everything I did from the start down was algebra. Now I get to do calculus. I get to actually evaluate my limit. So this one I am going to plug in 0. And so I'm going to get 1 over the square root of 4 plus 2, which is 1/4. So we just found the slope of the tangent line for this function at x equals 4. So if you use the second form, and again, I think I'll just let you trust me on this one. If you use the second form, you'll see that you get exactly the same slope. You're still going to have to rationalize. You'll have different things that end up canceling, but you will get to the same place. I promise. You know what? While we're here, let's get the equation of the tangent line. That's probably a good thing to review. I think it may have been, I don't even know if during the pre-calc review we really did one of these, but I mentioned the form that we need. So let's practice this, because this is something that we are going to want to do from time to time. Now that we've got its slope, let's get its equation. So to get the equation of a line, we're going to use the point slope form. So hopefully you remember this, the good old y minus y1 equals m times x minus x1. And in this, the m is the slope. So we just calculated that. That was 1/4. And then for the y1 and the x1, we need to have a point on our line. But the point on our line is going to be the point at the x that we were asked for. So that x is 4. Let me go ahead and put that in there. So we're going to have x minus 4. And then we get the y for that point by plugging in the 4. Well, the square root of 4 is 2. So for this one, we're going to use the fact that we're going through the point 4, 2. And we have a slope of 1/4 that we just calculated. And I'm going to go ahead and write it like you like it in the y equals form. This is going to be y equals 1/4 x plus 1. The plus 1 is what you're going to get after you distribute and shift things around. So not only were we able to find that slope at instantaneous rate of change, we were also able to find the tangent line. So that's not just the slope, but the line itself. So if you were to draw the graph of y equals square root of x and the graph of y equals 1/4 x plus 1, you would see this line just graze the square root. It would just graze it at that one point. So this is the process, and it doesn't matter what the function is. We just use that difference quotient and we evaluate a limit. So before I show you another one, how we feel about this guy. Is that all right? Not too bad? I mean, again, it's the square root of x, so it's the square root of x. But you're going to see that really what makes this complicated is if that function gets complicated, because that will change what you have to do. All right, well, let me give you another one here. And let's do exactly the same thing. So this time I'll even say, let's find the equation of the tangent line, or the line tangent, to f of x equals 1 over x at x equals -1. So very similar question. All I did was I changed the function and I gave you a different point, but the process is going to be exactly the same. So we need to pick which form of the difference quotient we want to use. And since we use the first one for the square root, let's use the second one for this guy. Let's use the limit as x goes to -1 of f of x minus f of -1 over x minus -1. So we'll just use this form this time. But again, the same thing, right? We're finding a slope, and then we're making it so that those 2 points, in essence, are the same point. All right, so let's put in our function, our specific values for this function. So f of x is 1 over x. F of -1 is -1. Right, 1 over -1 is -1. And let me take care of those minuses. Let's make those pluses. So we've got 1 over x plus 1 over x plus 1. So that looks a little bit better. But we still want to take this limit. All right, so what algebra are we going to do to this? Do you remember what you did with limits like this before? When you have fractions inside of fractions?
You try to multiply
Yeah, we're going to
with
multiply.
the denominator.
Yeah, let's multiply by the denominators of the inner fractions. Well, there's only one inside fraction. It's an x denominator. So we're just going to multiply everything by x. So on top, once I do this, I'm going to get 1 plus x, because the x times 1 over x becomes 1. X times 1, of course, is x. And then on the bottom, I've got x times x plus 1. And then, by the magic of algebra, 1 plus x and x plus 1 are the same thing, so I can cross those off. And so this is the same then as the limit as x goes to -1 of 1 over x. So now I can plug in my -1, and I get -1. So the tangent line to this curve has a slope of -1. So the instantaneous rate of change in this function is -1. So if we were looking for a velocity, it would have a velocity, instantaneous velocity of -1. All right, so this is the rate of change, which is the slope of the tangent line. They're exactly the same thing. All right, but I wanted us to find the equation. So let's go ahead and do that. So again, we're going to use y minus y1 equals m times x minus x1. All right, so let's start putting things in. We know the slope is -1. We just calculated that. We know the x-coordinate where we're looking is also -1, because that's what we were told. So the question is, what is the y-coordinate at -1? Well, take your x and plug it in here, and you see that it is also -1. All right, everything's -1. Cool. So this then gives us y plus 1 equals negative times x plus 1, which then if we distribute and everything gets us y equals -x plus 2. So there's the equation of your tangent line for 1 over x when x is equal to -1. All right, so how do we feel about that one? That one look all right?
It's kind of confusing that it turned out to still be 1 over x, because you couldn't have plugged in -1 at the beginning, right? Because we're not finding the limit, we're finding the slope.
Correct. So you're right that we couldn't have put it in at the beginning, and the fact that it did end up giving us 1 over x, yeah, it's just coincidence. Yeah, it happens sometimes. Sometimes weird, quirky things occur. All right, well, here's what I'm going to do. I'm going to go ahead and share my screen from my computer because I want to draw the graphs of these things. I want to actually show you that what we calculated in both cases, for both the 1 over x and for the square root of x, are actually the tangent lines. I want you to see it visually. So let's just do this one first. Just make sure everybody, you can see the Desmo screen.
Yes.
Okay.
Yeah. Bruce,
Cool.
I think the result is -x minus 2, not -x plus 2.
You are correct. Thank you for that, Fenrir. That one should be minus. So it's -x minus 2. So I just corrected it on the whiteboard screen. You'll see it when we go back. But so here's y equals 1 over x. You know that. That's the good old butterfly function. And now let me put in this one. So we have y equals -x minus 2. So you can see that these two functions, they do come together at that point, -1, -1, and it just grazes it. It is the tangent line at that point. All right, so there are those, and so we can see those. Let me put on the next one. So we did y equals the square root of x. Let me turn off these other guys. But we have y equals the square root of x. And then we were looking at, help me remember, was it 1/4? Or I mean 4 at x equals 4? So I'm pretty sure for that one we have the 1/4 x and then plus 1. Right? So that's the one that we found the other time. And you can see exactly the same thing. Like right here at this point, 4, 2, they do come together. But this line just barely grazes it before it moves on away. And locally, you can see that they look very much the same. Let me actually kind of move this more so that point is near the center, because I'm going to zoom in. Right? Let's think about this one point where they came together. So if I zoom in with this, near that point, so again, here's that point, notice how these two things are starting to really look the same. The green one is the square root of x. But eventually, if I keep zooming in, and I think the point of interest is right here, and I keep moving it towards the center, you're starting to notice virtually no difference. And that's kind of the point here, is that these tangent lines, they really are a good approximation for the function at that point. So where we're going to be going with this is anytime we've got kind of a crazy function, we can instead just approximate it with a line, because lines are easy. Lines are really easy. They're easy to draw. They're easy to calculate things with. And so if all we're looking for is a good guess, or a good guess locally, this will be perfect for us. All right, so any questions before I stop sharing that screen? All right. So hopefully you're buying that this is working. I mean, this is doing what we want it to do. It's getting us tangent lines. It's getting us instantaneous rates of change. So really, it's just a question of doing the limits. So I'm going to do one more, but this, and then we'll talk more about what's going on here. But I'm going to do one more, and this one more is going to be the one from the quiz, question number 2. Right? Remember, I asked you to approximate the instantaneous rate of change for that function. It was x cubed plus 2x, and I wanted you to approximate that at x equals 1. Well, now I'm going to show you how we can get the exact value using this technique. All right, so this was quiz number 2, or quiz number 1, question number 2. Okay, but this is going to get us exact value now. So we've got f of x equals x cubed plus 2x. So let's just dive in and actually calculate the limit. So I'm going to use the first one. Again, just sort of my habit. We're going to do limit as h goes to 0 of f of x plus h minus, or sorry, not x plus h, c plus h, minus f of c over h. Now, the c, we had a specific point, right? We were told we wanted to do this at 1. So we're going to have the limit as h goes to 0 of x plus 1 cubed plus 2 times x plus 1 minus x cubed plus 2x. And that's going to all be divided by h. Sorry, I keep putting x's. These are supposed to be h's. 1 plus h, 1 plus h, 1 cubed, 2 times 1. I apologize for that one. I was in autopilot mode. You'll understand later why I went where I went. But c is 1, right? We were looking at x equals 1. So c is equal to 1. And then I just plug those into my function. Now, this is going to require us to do quite a bit of algebra. we're going to have to cube and distribute and all that. So when you take 1 plus h and you cube it, you're going to get 1 plus 3h plus 3h squared plus h cubed. And then we're going to get plus 2 plus 2h. And then when I do the subtraction, I'm going to get minus 3. Just to show you where everything came from again, I'm going to use some color here. The first 4 terms, that was the 1 plus h cubed. The next 2 terms, ones with red, that was the 2 times 1 plus h. And then the 3 was just what we got when we calculated those numbers. All right, so I just did all that algebra crazy fast. All right, so now let's simplify this. So we're going to get the limit as h goes to 0 of, all right, well, let's just group them by terms. So I've got h cubed, 3h squared. I'm going to get 5h. And then in terms of the constants, I get 0. So that's everything on top. And that's still divided by h. Well, I can divide each of those things by h. So this gives me the limit as h goes to 0 of h squared plus 3h plus 5. And now I can let h go to 0. Those first 2 terms go away, and I'm left with 5. So you may remember that when I was going over that quiz, I told you guys, oh, well, the instantaneous rate of change for this one will be 5. Now we saw that. And when you guys did your approximation, you guys found numbers that were near 5. Like when I worked through mine, with that point, I got like 5.3 or something, right? So it was kind of close to 5 because my 2 points were kind of close together. But if I bring those 2 points really close together, as in having an infinitesimally small step, then I know my slope actually is 5. All right, so a couple things here. Just let's kind of be real about this. So first of all, here's some good news for you. The good news is this is always the same. The process is identical every time. I've now done for you like 4, maybe 5 examples. Every single one of them started out exactly the same way. I take the difference quotient, whichever form, it doesn't matter. But I take that difference quotient and I apply my function and my point to that difference quotient. Every time. Right? Then it's evaluate that limit. Every time. Now, this is where it does get a little bit different because the steps you need to take to evaluate that limit change, right? Like this one, I just had to distribute and group and stuff, and then next thing you know, it was something I could calculate. The one before, we had to multiply by denominators to get rid of fraction. The one before that, we had to rationalize. You're going to see ones where you have to factor. Like, I mean, it's going to run the gamut there. But it's always the same. Start with the difference quotient, then evaluate your limit. Okay, so there's some good news for you. But there is bad news, right? The bad news is there's a shit ton of algebra. There's a ton of algebra we have to do. There's a lot of things that we have to remember, right? And so there are lots of places where we can make mistakes along the way. So you got to pay really close attention to what you're doing. You got to be watching to make sure that you're doing the steps properly. You make one mistake early on, everything goes away. I mean, it runs into the ground. So you got to be really, really careful with these. Take your time. This is definitely a place where speed kills. If you try to do these too quickly, you will invariably end up screwing yourself over because you were going too fast. You made a mistake. You're going to have to go back and find it. And by that point, you're spending more time. Okay, so especially at the beginning, go slow. All right, well, I don't want to leave you with just bad news. Right? So let me go back to some more good news. And this is actually related to the first good news, right? The first good news was it's the same process every time. So here's how a mathematician thinks. Mathematician goes, hey, you know what? I'm having to do the same thing every time. So how about I just like do it generically? How about I just do it one time so that I don't have to do this tons of times? Because if I do it once and I get a nice little formula or procedure, I never have to do it again. A great example of this that you've seen before was the quadratic formula. You all remember that one, right? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a, that thing. So we use that a lot, right? When you're trying to solve a quadratic. But where it came from was completing the square. Now, I think I probably just triggered some of you by saying completing the square. You just had horrible flashbacks. Completing the square sucked. Oh my gosh, it was horrible. All the steps you had to do and everything. Well, the quadratic formula came from, well, let's just complete the square one time generically. Let's not put in any numbers. Let's just keep the letters A, B, and C. And the next thing you know, the quadratic formula spits out. And then you never have to complete the square ever again to solve a quadratic. Right? So this is a trick mathematicians do all the time. And I'm going to show you how we can do that with these guys. Because like this one, this was great for finding the rate of change at x equal 1. But what if I also want to know the instantaneous change, rate of change in this function at x equals 5? And also x equals minus 2. And, you know, I give you a list of like 20 of them. Are you going to want to do 20 of these? And you don't have to answer that question because I know the answer for all of you is no. I mean, I don't want to have to do 20 of them. But I can recognize that, well, it's going to be exactly the same every time. So what if I just leave it as an unknown point? Can I somehow get to the same thing where now I have some sort of a formula for finding my rate of change? And that's definitely what we're going to do. So I don't want to do it with this function because this function is a little bit nastier than I actually want to apply it to. So let's take another function, and I'll show you how we can do this in a just always the same, here's how we get it kind of way. All right, so how about we do this? Let's find a formula for the rate of change, the instantaneous rate of change for f of x equals, and you know what, let's do x cubed. So just a real basic polynomial. It's not just x squared, it's a little bit more complicated, but let's look at just x cubed. Okay, so let me show you what I mean now. We're going to use that same formula, the m tan. So I'm going to do the limit as h goes to 0. But now, instead of having c plus h, I'm going to write x plus h. And instead of c, I'm going to write x. So if you go back and you look at how we define this, so just go back in your notes a couple of pages, you'll see that the only difference here with what I've written versus what you have in your notes is that I wrote x instead of c. Because I don't want to specify the point. I'm looking for, is there a way that I can get a formula so that now when you give me the point, I just plug it in. Okay, so let's just go through the motions with this and let's see what happens. Let's see if something falls out. So we're going to get the limit as h goes to 0 of x plus h cubed minus x cubed over h. So I'm just plugging into my function x plus h. So x plus h cubed. And then I'm subtracting the original function. All right, so now let's multiply that out. So if you were to take x plus h and cube it, you're going to get x cubed plus 3x squared h plus 3xh squared plus h cubed. And a real quick aside, some of you may be seeing me do these like powers and go, holy crap, where's that coming from? Obviously, because I do these a lot, I know them off the top of my head, but there is a fast way. When you have a binomial raised to a power, it's called the binomial expansion theorem. It's a pre-calculus thing that you probably saw at some point. I'm going to recommend you maybe go back and look at that because it's super, super useful. But there's definitely a pattern. Let me just show it to you really quickly. Notice that my two things were x and h. If you look at the first one, x, notice that my powers, I started with an x cubed, then I got an x squared, then I got an x, and then I got no x's. And the h's, the pattern is reversed. No h's, 1, then 2, then 3. And that's always the case with your variables. The first one will start with the same power as what's on the outside and then work its way down. And the second one's going to start with the power of 0 and work its way up. And then the numbers, the coefficients here are 1, 3, 3, and 1. Those come from Pascal's triangle. Pascal's triangle is the one that starts like this. And basically the way that you find the next row in Pascal's triangle is it starts and ends with 1, but then every other number is the sum of the two that are above it. Right, so looking at this row, notice that the 4 is 1 plus 3, the 6 is 3 plus 3, this 4 was 3 plus 1. You can create the next row the same way. So like this next row is going to start with a 1, then we're going to get a 5 because that's 1 plus 4, then we're going to get a 10, 4 plus 6, 6 plus 4 is another 10, 4 plus 1 is a 5, and then a 1, and so on and so forth. And so you always just use the same row. You use the power to tell you which row. So since this is a cube, I'm going to start with the one that goes 1, 3. If it was x plus h to the 5th, I'd start with the one that's 1, 5, and so on. So if you don't like know about that, or if you're going, whoa, I've never seen that before, look it up. Binomial expansion theorem or the binomial theorem. It's a biggie. It's a huge time saver. Or pop into office hours and we'll chat about it. Okay. Anyway, so that's what you get. It's way faster than doing FOIL over and over and over and over. So let's simplify this. We've got x cubed minus x cubed. I'm going to go ahead and slash those. So now we've got the limit as h goes to 0 of 3x squared h plus 3xh squared plus h cubed over h. Just like with that other one, I can divide the h's, divide by h. So we get the limit as h goes to 0 of 3x squared plus 3xh plus h squared. And now, if I let h equal 0, My first term is still going to be 3x squared. So I'm going to put this up here because we have a 3x squared. The second term, when h is 0, this goes away. 3 times x times 0 is 0. H squared, also 0. All right, so check it out. We have a formula now that tells us the slope of the tangent line anywhere. And if you don't quite see the power of this yet, go back to my original, like why I suggested this. What if I wanted to find the instantaneous rate of change at 20 different places? Well, now I would just have to plug in that number. All right, so here you go. Here's going to be a list. Suppose that this was the list of places I wanted to see. All right, so I'm going to make a little chart here. I'm going to put x, and we're going to put slope of the tangent line here. So here are some x's that I'm curious about. Let's say 3, -1, 0, 10. We'll just do these 4. All right, well, if you want to know the slope of the tangent line at those different places, we're just going to plug those into this formula. So I plug in 3. 3 squared is 9 times 3 is 27. So out there at x equals 3, the slope of the tangent line is 27. It's pretty steep, going in a positive direction. All right, at -1, -1 squared is 1 times 3 is 3. Okay, how about at 0? 0 squared, 0 times 3 is 0. How about at 10? 10 squared is 100 times 3 is 300. Ooh, that's really steep. All right, but did you see how fast that was? I was able to give you, just like rattle off the slopes of tangent lines because I did all of the work once, right? No doubt this was the bulk of the work. Actually doing the limit, that's where I did almost all this work. But once I got to this, here's the formula, it was fast. And that's the dream of every mathematician. We just want to get to a point where we don't have to work anymore. We just want to take it easy. Right? That's why I think I'm actually a good mathematician, because what do I want to do on the weekends? I want to watch football and drink beer while I'm sitting on my sofa. I don't want to do extra work. So I do all my work ahead of time so that I can take it easy, right? Same thing here. I did all this work ahead of time so that then I can take it easy. All right, so if you're anything like me, and most people have a little bit of laziness in them, you're going to be a great mathematician. As long as you're willing to do the work up front so you don't have to do it later, that's quality of a mathematician for sure. All right, so was there a formula? Yeah, absolutely. It's also dependent on x. It depends on where we are, but that kind of makes sense because we've seen that the slopes of tangent lines or the rate of change, they change as we move around, right? So it's another function, but this function, actually, we give it a name, all right? And this is what we call the derivative. So you may recall that when I gave you sort of the preview of calculus, I said there are two things we're going to do. One is differential calculus, the other is integral calculus. Well, this is differential calculus. Differential calculus is all about finding derivatives. So let me kind of formalize this for you, give you the notation so that you can see what we're going to have. All right, but we call this the derivative. So first things first is that this is a function. Okay, it is a function that's related to f of x. So when we talk about a derivative, it's always a derivative of another function. Okay, it's kind of like inverses. Remember with inverses, it was always what's the inverse of this other function? Same thing with derivatives. It's going to be what is the derivative of this other function. Okay, so it's a function that's related to f of x. What it tells you is it's basically the formula for the slope of the tangent line. So like this one, when we got 3x squared, it was the formula that was going to give us the slope of the tangent line for whatever x that we plug in. All right, but I also want you to realize that anytime I say slope of a tangent line, that also means instantaneous rate of change. So I want you to start getting used to those three things all meaning the same. Okay, so I'm gonna write here in a different color that derivative equals slope equals rate of change. So if you're asked to find the rate of change, it's the same as being asked slope of the tangent line, same as being asked derivative. So these three things are all interchangeable. Depending upon the problem, depending on the context, you're going to be asked for one of them. But it's really useful if we just kind of have it, oh, these all mean the same thing. You know what tool to go to. Okay, so derivative means the same as slope. It's the same as the rate of change. Okay, so the derivative is a function, and it does give you the slope of the tangent line. And in terms of its notation, the way that you're going to see that you need to take a derivative, or this function is derivative, is we're going to write f with just a single marking up here. Kind of looks like a 1. It's not a 1. It's actually just a little bit of an angle. It's an apostrophe, basically. So we have f with this little apostrophe of x. Okay, so this is the notation you're going to see. If you ever are asked to find this, that's saying find the derivative. Okay, now the way that we say this in words is we say f prime of x. So anytime you've got that apostrophe, that little tick mark up there, what we're going to say is that that's f prime of x. All right, so finding the derivative, finding f prime, same, but it's that find the formula that gives us the slope of the tangent line for a given function. All right, so let's do this. Let's find some more derivatives. Let's find some more of these formulas for other functions. And in fact, let's actually go back to some of the functions that we've seen, that we calculated the slopes of tangent lines at one specific point. But let's actually find their derivatives. So I'm going to make a chart over here that has functions and their derivatives. And I'll try to avoid the glare. So I'm going to have f of x and f prime of x. Oh, and I'm totally heading right into the glare. Let me write it down lower. And I'm going to put the one that we just did. So we started with x cubed and we found its derivative was 3x squared. Okay, so we're just going to keep that as a rolling list as we do more of them. All right, so let's try this for another function. Let's try f of x equals the square root of x. So we're going to try to find f prime. So what we're going to do is we're going to use the limit, just like we did before. And again, instead of plugging in a c, we're just going to leave it as x. So it's going to be the limit as h goes to 0 of f of x plus h minus f of x over h. So if I put this into our specific function, we're going to have the square root of x plus h minus the square root of x divided by h. All right, so this is the limit we have to evaluate. And like I said before, don't bother plugging in 0 because you're just going to get 0 over 0. So let's dive right into algebra. So for this one, the algebra is going to be multiplied by the conjugate. So we'll multiply top and bottom here by the conjugate, which is going to be the square root of x plus h plus the square root of x. All right, so on top, we're going to get a difference of squares. So when I FOIL it out, the first one squared gives me x plus h. The last one squared gives me x, but I subtract them. So I'm going to get x plus h minus x. So on top, those x's cancel, because I've got x minus x. And I also can now cancel those h's. The h on the bottom cancels with the h on top. So I'm left with the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. So there was quite a bit of algebra in here. I didn't list out every step. If you're not sure about it, come find me in an office hour or something and I'll walk you through it. But now I'm ready to plug in 0. So if I plug in 0, I get 1 over the square root of x plus the square root of x, which is 1 over 2 root x. And so now I can calculate the slope of a tangent line anywhere. And look at what we did with that specific function. We looked for the slope at, I believe it was at 4. Plug a 4 in here, and you'll see that we get 1/4, which was the same slope that we found before. But now I could also do it at 100. Plug in 100, I get 1/20. That's the slope when we're out at x equals 100. What about at 1? Square root of 1 is 1. So 1/2 is the slope at x equals 1. And notice how I can just rattle them off now. You give me an x value, I just plug it in here, slope of my tangent. You may not really appreciate that, but trust me, this is nice. This is really nice. All right, so here's another function. Then we have the square root of x. And we just saw that its derivative was 1 over 2 square roots of x. So let's try another one. Let's try f of x equals 1 over x. So this is another one that we did just a minute ago. So let's see if we can figure out what its derivative is going to be, what the formula for slope is. But before I dive in there, any questions on this one? You kind of on it? All right, so let's try 1 over x. So I'm going to use the same definition for f prime. Right? This doesn't change. The only thing that changes is the function that we're plugging it into. So this becomes 1 over x plus h minus 1 over x divided by h. So like I just said, it's the same form, exactly the same form. just putting it into a different function. All right, so this one, since we've got fractions, the trick is to multiply by the common denominator, which is going to be x times x plus h. So we'll do that on top and bottom. When I distribute, the first one, the x plus h's cancel. So I'm left with just an x. For the second one, the x's cancel. So I'm left with an x plus h. And on the bottom, I've got x times h times x plus h. So now I'm going to distribute. I'm going to pass that minus sign through. So I'm going to get x minus x. Those go away. But then I also have a minus h. Let me put that up here. On the bottom, I've got xh times x plus h. And now I can cancel those h's. So I'm left with the limit as h goes to 0 of minus 1 over x times x plus h. So this one I can now plug in 0, and I'm left with 1 over x times x, which is 1 over x squared. So here is the formula for the derivative of 1 over x. So I'll put that on our chart over here. We had 1 over x. We just thought its derivative was 1 over x squared. And if you were to go back and look at what we did, we wanted to find the slope of the tangent line at -1. Well, if you plug in -1 here for x, you get a slope of -1. But again, the beautiful thing of this is now I can just do tons of them. You give me an x, I just plug it in, and I can tell you the slope of the tangent line like that. All right, so it's one we've already done. And at this point, you're probably going, well, this is great. You just keep doing the same stupid ones over and over and over. So how about we do a completely different function, one that we've not tried before. All right. And I'm going to ask you to find the slope of the tangent line at lots of places. Okay. So here is the question for this one. I want to know, what is the slope of the tangent line, or the line tangent, to f of x equals sine of x, but I want to know it at x equals 0, x equals pi over 2, no, pi over 4, x equals pi over 2, and x equals pi. So I want 4 of them. I want to know the slopes of the tangent lines at those 4 places. So think about what we could do. We could tackle each one of them separately, go back to the definitions that we first used, put in these numbers as our c's, sine of x as our function, and go. Or alternatively, we can just do it generically, find the derivative, and then once we have that formula, plug in these numbers. Okay, so I'm going to pick the second option. Let's do all that work once. Let's actually just find the derivative and then evaluate that derivative at these 4 points. All right, so here we go. Do the same thing that we've done every other time. F prime of x is the limit as x goes to 0. H goes to 0. F of x plus h minus f of x over h. So for this one in particular, this is going to be the sine of x plus h minus the sine of x divided by h. So I just want to pause for a second because I want to point this out again. You're probably feeling like I keep hammering the same nail, and I am. Same formula, just different function. If you go back and you look at every single one of these, they all start the same way. I mean, that's the beauty of this. It's the same process every time. We just put in the different function, and when we get to that function, we have to go to the, all right, well, what do we do with this function? All right, well, what do we do with this function? How do we simplify this guy? Because you think about the tricks we know, factoring doesn't apply here. Rationalizing, no radicals. Multiplying by denominators, no fractions. Like all the tricks that we've used so far, none of them apply. So what do you guys think we can do here? Any ideas? All right, so sum to product identity. Oh, I love that. Nobody ever thinks about that one. All right, so Mariola just put in there the sum to product identity. I don't know if you guys remember such an identity, but when you have sums and differences of sines and cosines, there's a way to write them as a product of sines and cosines. So that's the sum to product identity. And that would totally work. That would totally work, Mariola. I'm super impressed. I don't think I've ever had anybody suggest that one before. So you get extra special bonus points. They're not worth a lot, but maybe a smile.
Just because I just took the trick, that's why, you know.
Because it's relatively fresh in your mind.
Yeah.
We are going to want to use an identity, but the one that we're going to use is we're going to use the sum of angles identity. Because inside this sign, we've got two things being added, right? X plus h. So I'm actually going to use that one. I'm going to use the sum to product. But the product, or sorry, not sum to product, the sum of angles identity. But you're right, Muriel, the sum to product would work. All right, so let me just remind you the sum of angles identity. So this one, you end up getting the sine of x times the cosine of h plus the cosine of x times the sine of h. So again, these guys right here, that was the sine of x plus h. All right, so that's just using that sum of angles identity. And so then the next step I'm going to do is I'm going to get all the ones that have sine of x and kind of put them together. And the cosine of x, I'll put those together elsewhere. Right, so I'll just kind of split this up. So let me start with the cosine one. So we have cosine of x times the sine of h over h. So that was that middle term. And then we're going to have plus sine of x cosine of h minus sine of x over h. So I did this on purpose. I did split it this way on purpose, and you'll see why in just 1 second. Okay, so let me, with this second set, factor out the sine of x, since it's in both of those terms, and then we'll be ready to actually evaluate our limit. So we've got the limit as h goes to 0 of cosine of x times sine of h over h plus sine of x times cosine of h minus 1 over h. So for that second one, I literally only factored out the sine. All right. So now, turns out we can evaluate that limit. So remember, we're only looking at the pieces with h. That's the only part that actually matters in terms of evaluating the limit. So I'm going to have cosine of x. That's constant with terms of h. It doesn't change.
Why aren't that cosine and sine x over h also?
I mean, I do. I just wrote the cosine out front because I can.
Oh, okay, gotcha.
Right, because it could be like cosine x over 1. Really, I wrote it this way just so that I can get the pieces that involve h together. Right, when I'm doing the limits, I really only care about the stuff that's in the parentheses in both ways, right? So it really is the same thing. I just wrote it slightly differently. Okay, but now what about this sine h over h? What happens to that as h goes to 0?
Is equal to 1.
It goes to 1. So we proved this one the other day, and it was one of those I said, hey, know this. And this is why. Sine x over x, as you go to 0, that goes to 1. So sine h over h, as that goes to 0, as h goes to 0, that goes to 1. So we're going to get cosine of x times 1. The next limit, we're going to get sine of x times something. Well, what happens to cosine h minus 1 over h?
Does it become 0?
That was another one I showed you. What was that, Susanna? I'm sorry.
Oh, I said, does it become 0?
Yeah, that one goes to 0. So that was another one that we proved. It was one that I didn't say you should know because it doesn't show up as often. But we did actually do that one. So we know that that actually goes to 0. So we're left with cosine of x times 1 plus sine of x times 0. Well, that's just cosine of x. So the derivative of sine of x is cosine of x. Weird. But yeah, the cosine is going to give us the slope of the tangent lines to sine. And now that I've got that, watch how fast this is to find the slopes of the tangent lines. So I'm going to make a little chart here. Going to have x and m tan. But we're putting in 0, pi over 4, pi over 2, and pi. All right, here you go. Cosine of 0, 1. Cosine of pi over 4, root 2 over 2. Cosine of pi over 2, 0. Cosine of pi, -1. Fast. Well, I mean, okay, it requires knowing the trig values, right? But it's quick. It's way faster than trying to do this sum of angles garbage 4 different times with 4 different angles, right? We can do this quick. And that's kind of the whole point of the derivative, is getting us a function where we can find these slopes of tangent lines in a much more expedient manner. All right. I think I'm going to stop here because we're pretty much out of time. But where we're going to head, well, let me just do this for you. Yeah, I'm all excited about, we've got the same thing. We can just do it once and call it good. It's still a pain in the ass. right? Getting down to finding that this derivative was cosine required all kinds of trig and algebra stuff that was a lot, right? Well, there is a faster way. And where we're going to go next is I'm going to show you a faster way. We're going to develop rules. We're going to make this even more generic. We're going to develop some rules that make it so that finding derivatives is crazy fast. Like after the next day, after was that Friday, we're not going to use this difference quotient stuff. We're not. We're going to use these faster rules. All right, so basically we're going to use the difference quotient one time to help us get more generic rules, and then we'll have a fast way of finding derivatives. Okay, so that's where we're going. Also wanted to remind you that we are having a quiz on Friday. So we're at that point again. So the quiz on Friday is going to cover the sections on limits and continuity. So basically what we talked about last week's homework. So I don't remember exactly what sections those are. They are from chapter 2. So basically it's from chapter 2. Okay, so the quiz on Friday will be on chapter 2 stuff. We'll do it exactly the same way. It will turn on at 8:30. It will be due by 9:10. And then at 9:10, we'll come back into the Zoom classroom and do more stuff, okay? So just be ready for that. And then also just a reminder that there are homeworks out there that you can work on that are gonna be coming up due on Monday night. All right, so with that, I'm gonna go ahead and stop our recording.